In the previous video, we discussed vectors, vector addition, vector subtraction, and, most importantly, vector decomposition. In this video, we'll examine a special case of vector decomposition, a special vector notation called Cartesian notation, and in the second part of this video, we'll extend both to three-dimensional vectors. Recall that vector decomposition is the process by which we take a vector, in this case vector C, and convert it or represent it as two vectors, one pointing in an arbitrary A direction, the other pointing in an arbitrary B direction. Another way to say this is that we're looking for the vectors, or the magnitude of the vectors A and B, which will satisfy this equation. C is represented as B plus A. What happens if the two directions that are selected are orthogonal to each other? Orthogonal lines, so this would be A direction, this would be the B direction. Orthogonal lines form right angles. Here we see that what happens is when we form the triangle to do the decomposition, it's a right triangle. When we draw a vector, we need two items, the magnitude and the direction. The magnitude is the length of the arrow, and the direction can be provided in two ways. The first is to provide an angle to a reference. So in this case, we have a horizontal reference line, and we've provided the angle to that reference line. Since that horizontal reference line in this particular case is also the A direction, that corresponds to this angle. In this case, we can find the magnitudes of vector B from the law of sines, and the magnitude of vector A from the definition of the cosine. You should remember this from trigonometry. Another way to define the direction is to indicate what the rise of the vector is with relationship to the distance traveled. This is basically the slope of the vector. So when we do this, we draw a small triangle next to the vector, and we indicate what the rise is. In this case, it might be 3 over the slope, or excuse me, over the distance traveled in the reference direction. As we all know, this triangle is also a right triangle and is a 3, 4, in this case, 5 triangle. So quite often we'll see these little triangles and no indication of what the angle is. Again, both of these representations provide the same information. They're giving us information about the direction of the vector. When we have this type of information, we can recognize that this triangle and this large triangle are similar triangles, and we can calculate the magnitudes of vectors B and A from this formulation. B is 3/5 the magnitude of C, and the magnitude of A is 4/5 the magnitude of C. So now that we can decompose a vector into two orthogonal direction vectors, we can use some special notation. If we say that this direction, which we've previously been calling A, is the x direction, and this direction that we've previously been calling B is the y direction, you should now be able to recognize that the A vector, which points in the x direction, can also be called the C x vector. So we'll rename A as Cx, and B as, not surprisingly, Cy. Now we can say that C is equivalent to Cx plus Cy. We might call these the component vectors, Cx and Cy, of the total vector C. I'd like to point out real quickly, if you haven't noticed, that the book uses bold characters to indicate vectors, and non-bolded characters to indicate the magnitude of those vectors. Here what I've done is I've tried to use bolding with an arrow over it to indicate a vector, and not bolding and without an arrow over it to indicate the magnitude. These equations provide no information about the direction, only information related to the magnitude of the vector. So you have to go back and still use this triangular formulation to determine what the actual directions are of A and B, Cx and Cy, are in relation to the positive x and positive y axis. There's another notation that we can use that utilizes the concept of unit vectors. A unit vector has a length of 1. And if we place a unit vector on the x-axis and a unit vector on the y-axis, and call the unit vector on the x-axis I, and the unit vector on the y-axis j, we can now represent Cx and Cy vectors differently. So now we can say that Cx, the vector Cx, is equal to the magnitude of Cx times the vector I. And Cy, or the vector Cy, is equal to the magnitude of the vector Cy times the unit vector j. This means that we can represent our original vector, C, a little bit differently. So our vector C can now be represented as the magnitude of the x component of the vector C times the unit vector I, plus the magnitude of the y component of the vector C times the unit vector j. And this is called Cartesian notation. And this is the notation that we'll start very quickly to use throughout the book. The advantages of this notation are twofold. First, if I have a vector C that I claim to be the sum of two vectors, Q and P, to determine this addition, I can first write that the vector of Q is the magnitude of the x component times I plus the magnitude of the y component times j. Doing similar with P, I can write that that's the magnitude of the x component of P times I plus the magnitude of the y component of P times j. Since addition of vectors is commutative, I can then write that C is Qx plus Px times I plus Qy plus Py times j. Again, both of these are unit vectors. If we have vectors written in Cartesian notation, if I already have this notation determined, I can find out specific information relating to this vector C by using the law of cosines and the definition of the tangent. For example, if I want to know the magnitude of the vector C, I simply use the law of cosines, which tells me that C, in this case, is Cx squared plus Cy squared. The definition of the tangent says that tangent of some angle theta is equivalent to the opposite over the hypotenuse. In this case, that's Cy over Cx, where theta is the angle that the vector C makes with the x-axis. So what we can see is if we can get vectors into this Cartesian notation, it makes doing the math much simpler, We don't have to fall back to trigonometry to actually do the calculations. So we've just learned two new ways of writing a vector. The concept of writing out two vectors that point in the x direction and the y direction, and using the concept of unit vectors to be able to write a full Cartesian notation formulation for any given vector. We've done this in 2 dimensions, but we could extend this to 3 dimensions without too much effort. The first issue that we have to face in 3 dimensions is that there are actually a couple of different ways to write the coordinate system. So I've shown the 6 standard ways of writing the coordinate system here. You'll notice that if you take one of the representations on the top row, you can rotate it to obtain any of the other 2. However, you cannot take any of the representations on the top row and rotate them to form any of the representations on the bottom row. These 2 rows are fundamentally different ways of labeling the coordinate directions. This is a right-handed system, and this is what we might call a left-handed system. So the right-handed system is the system we will use in this class, and indeed is a system that's followed in most modern engineering textbooks. You can identify a right-handed coordinate system by doing this. Orient your body in space so that it points in the z direction. Stand facing the y direction. If you're looking straight ahead, you're looking down the y direction, and hold your right arm out, and you'll be pointing your finger in the x direction. On this particular case, you'll lay on your back looking up with your right arm extended this way, and in this case you'd lay on your left side looking this direction and your right arm pointing up. Now that we've learned to draw and recognize right-handed coordinate systems for 3-dimensional space, we can draw vectors in 3D space. So here I've drawn the vector C, and I've added this gray box to help your eye understand which direction the vector C is pointing. Now we can go a step further and say, well, this vector C is actually the sum of a vector that points in the x direction, a vector that points in the y direction, and another vector that points in the z direction. So one way of representing vector C is to say vector C is Cx plus Cy plus Cz. Furthermore, we can extend our concept of unit vectors to include that 3rd dimension. So here's a unit vector I, a unit vector j, and we would have a unit vector k in this direction. Now we can represent C as the magnitude of the x component of C times I plus the magnitude of the y component of C times j plus the magnitude of the z component of Z times k. Once we have this representation, we can actually extend our equation for determining the magnitude of C, and we can now write that the magnitude of C is equal to the square root of Cx squared plus Cy squared plus Cz squared. Directions, unfortunately, are a bit trickier. In 2 dimensions, we only needed to define the angle that the vector made with the x coordinate direction, and we called that theta. In 3 dimensions, we usually call that angle alpha. Once we had that angle in 2 dimensions, we could readily find the coordinate angle that the vector made with the y-axis. In this case, we can't. Here we actually have to specify that angle as beta. The angle that the vector makes with the z-axis is called gamma. So now we have 3 coordinate directions. I'll show you in a minute that we really only need to define 2 of these angles, and there's a way to determine the 3rd. In order to see that, let's recognize how we would calculate any of these given angles if we had both the magnitude of C and the magnitude of each of these directions. If we draw a line that connects the 2, you should recognize that each of these angles is a right angle. That means that the cosine of alpha equals the magnitude of Cx over the magnitude of C. the cosine of beta is the magnitude of cy over the magnitude of c, and that the cosine of gamma is the magnitude of cz over c. So if we go back to the concept of unit vectors, we would say that a unit vector in the c direction has a magnitude of 1, but the same direction as c. So we can write that as c vector divided by its own magnitude. So that means that that is cx over c times I plus cy over c times j plus cz over c times k. These terms define the cosine of the coordinate directions. So UC can actually be written as cosine of alpha times I plus the cosine of beta times j plus the cosine of gamma times k. And you should now recognize that the magnitude of u, or the magnitude of UC, should be equal to 1 because it's a unit vector. But how do we determine the magnitude of the vector? It's simply the square root of the I component squared plus the j component squared plus the k component squared. So you see that this equation relates the 3 coordinate directions. So you only need to define 2, alpha and beta, or alpha and gamma, or beta and gamma, to fully represent the direction of the vector c. So UC is the vector c divided by its own magnitude. It turns out that that can be simplified to this using these relationships above, and we have this particular equation. We can rewrite this portion of the equation and write that c can be written as the magnitude of c times UC. We can actually explicitly write out the unit vector, or we can explicitly write it out as we have above in full Cartesian notation. Cxi plus cyj plus czk. What I want you to note from these two systems is that you only need 3 pieces of information to fully define both the magnitude and the direction of the vector. So if we look at the Cartesian notation, well, you'll see that we can determine the magnitude of the vector using this formula, and we can determine any of the directions using this formula. And so if we have this information, cx, cy, and cz, to determine the magnitude, we certainly have it also to be able to determine the coordinate directions. If, on the other hand, you're provided this information, you still only need 3 of these pieces. You need the magnitude, but you only need 2 of these angles to be defined for you. That's because you can find the third angle using this equation. Now that we recognize that we only need 3 pieces of information to fully describe the vector, and that 2 of them actually are related to the direction in 3D space, we sometimes are provided slightly different types of information that we have to learn to convert to those 3 coordinate angles. So for example, sometimes we're given the coordinate angle that the vector makes with one of the axes, in this case z, but instead of being given one of the other angles that the vector makes with an axis, we're instead given a projection of the vector in 3D space onto a plane created by the other 2 axes and the angle that that projection makes with one of the axes. So in this case, we might be given theta, the angle that the projection makes with the x direction. It takes a little bit of algebra, but it would be good practice and good learning for you to learn how to convert this sort of representation into alpha, beta, and gamma. So there's geometry involved, but you can determine alpha, beta, and gamma from these pieces of information. We've learned that the small triangle also represents direction. So sometimes we may instead be given a small triangle representation, 3, 4. Or indeed we may be given a small triangle representation for both pieces of information, 3 and 3, for example. Once you have that Cartesian notation, it makes doing a lot of the math in this class much easier. The first thing we'll talk about, obviously, is addition. So if you have the Cartesian representation of C and R, you can find the Cartesian representation of F directly by adding those coordinate magnitudes. This is also going to be important when we get to the concepts of the dot product and to the concepts of torque. So the Cartesian representation of vectors forms the foundation of mathematics we will use in the rest of the course. Please practice taking vectors represented in various graphical ways, using angles, slopes, combinations, etc., and writing them in Cartesian notation and in magnitude times unit vector notation. In addition, please make sure that you can draw and recognize right-handed coordinate systems. And as always, please come see me if you have any questions.